So if you look at the Corvallis volume, the second volume, second to last paper, you'll find a paper by Kashtan with basically the same title. A very inspiring 10-page paper, very dense, with a sketch of the proof of Drinfeld's theorem for Langlands over global Langlands for GL2 over a function field. The only problem is that till the end of the paper, there's no definition of Shtukas. So I think 45 years have passed. We've made so much progress. At least I'll try to give a definition today. Okay, so fix some notations. So I'll work with a fixed complete geometrically connected curve over a finite field FQ. F denotes its function field. And we'll freely use familiar notations like these completed local rings and local fields, residue field. So this is for any place or close point on the curve. We have these local notation. And G will be fixed to be a split reductive group, connected reductive group over K. Okay, so the goal of automorphic form theory for function over a function field is, of course, to study how G of Adels act on functions on this adelic quotient. So, but we are going to interpret these kind of function theoretic notions in terms of more geometric language. So this is already, for GLN, this is already mentioned in Pierre Henry's talk this morning. So let me just restate it, this Wei's dictionary for split reductive group. So on the one hand, we have this double coset space. Here K is a product of G of OV, OX, maximal compact subgroup, standard level structure. On the other hand, we have G bundles on X. So both sides are groupoids. So here it has objects, G bundles, and then isomorphisms as morphisms. Here it's a groupoid made by quotienting a set by a group action. Right? So we can, if I think of this as the set I'm quotienting by, so G of F acts on it with stabilizers, and those stabilizers are the automorphism groups in this groupoid. So this is an equivalence of groupoids. Here I'm using that G is split. This statement is extremely clean. In general, the right-hand side is slightly bigger than the left-hand side, but let's not worry about it now. So when we study functions on this double coset, we can naturally interpret them as functions on G bundles. For each G bundle, I give a number. So this is the kind kind of a geometric point of view. But we want to geometrize it a little bit further. We want to consider not just G bundles as individual objects, but we want them to move in moduli. Okay, so this bund G will appear is a fundamental geometric object in the subject. This is the moduli stack of G bundles on X. So let me give a more precise definition. And this style of definition will appear over and over again in these lectures. So to give you a stack, I need to tell you its functor of points. So I take a test scheme. All the schemes in this talk are over FQ. So then the output will be an S family of G bundles on X. More precisely, an S family of G bundles is just a G bundle on the product over FQ. I will not write down fiber over FQ. So it's a G torsor over the product, and again viewed as a groupoid. So this is the functor of points defined by bund G. And important fact is that this bund G is an Artin stack, or an algebraic stack. Locally of finite type, and in fact smooth over spec K. Okay, so it's more or less like our favorite smooth varieties, except that points here can have positive dimensional automorphisms. For example, the trivial bundle here has automorphism by the whole G. That's viewed as a continuous group rather than a discrete one. So just to be more concrete, let's look at some examples of G. So for GLN, of course, when we talk about GLN bundle, this is just a vector bundle. So there is a natural correspondence between principal GLN bundles and vector bundles. So moduli stack of vector bundles of rank n. Well, okay, so dictionary works. So we have a vector bundle, then say over X. Then you take the frame bundle. The frame bundle is just isomorphisms between the trivial bundle, local isomorphisms between the trivial bundle and your bundle. This shiftifies over X and becomes a principal bundle for GLN. Okay, and in the other direction, you take principal bundle, and there's a construction called associated bundle to a representation of a GLN. So what it means is you take this total space E cross standard representation V standard. This is just an affine space with GLN action, and then you quotient by the diagonal action of GLN acting on both sides. So this gives you a vector bundle over X. For classical groups, we can always think of bund G, when G is a classical group, as as a vector bundle with auxiliary structure. For example, so this bund SP2N is classifies bundles rank 2M rank 2m bundles together with a symplectic form. So this symplectic form means there is a pairing, perfect pairing. So everything is over x times s. This is an alternating in the usual sense and perfect pairing. So again, this is not literally the definition, but you can use the same idea to pass between the principal bundle and the vector bundles with extra structure. Okay, so that's the bund G. Now, I will introduce Shtukas in several level of complexity. So basically, first I will introduce Shtukas with one leg and no bound. So I'll explain what these things mean. And next, I will introduce bound, one leg, and then more legs, and the variants called iterated versions. So I think you should feel very much satisfied if you understand the one leg case with a bound. And the other more complicated versions are not so urgent. Okay. So I need to, before introducing Shtukas, we need to talk about Hakka modifications. So the Hecke stack is a correspondence between bund G and itself. And it also maps to maps to the curve. So in terms of functor of points, what it classifies, of course, since it maps to all three guys, we need at least 3 pieces of data. That is a point in X, 2 bundles. And then, most importantly, is the last piece, which is an isomorphism between E restricted to, so both E and E prime, they live on this product space X times S. I only require an isomorphism on open subsets of this product by removing the graph of X. So what this means is X is a map from S to X. You can think of S is just a spectrum of a field. This will give a field-valued point in X, and then I can talk about its graph. It's a copy of S, but diagonally embedded in S times X using this map. Okay. Again, this is just a point if S is a point. So an isomorphism away from one point. The only, so this should be a familiar to you if you, for example, if you're familiar with modular curves. This, at least for a fixed point X, this kind of modification is analogous to isogeny. Well, p-isogeny for a fixed p between elliptic curves. The only little extra thing here is that this X is also varying. Okay, so that's mapping Hecke to X. Okay, so this is also a stack, but it's not as nice as Bun-G. In particular, it's infinite dimensional. Okay, so this is a kind of not of finite type, not even locally of. Well, it's so more precisely, this is a well, infinite union of algebraic stacks. It's too big. Later, we will put a bound to cut it into finite dimensional objects. Right now, it's basically a symbol, which is convenient to define kind of the essential part of Shtuka. Okay, so now we can already define Shtuka. So Shtuka G, so maybe decorate it a little bit by G, with one leg. Is defined by the Cartesian diagram. So Hecke G mapping to Bun-G times Bun-G. And then I pull back via the graph of Frobenius. Okay, so in this diagram, out of 4 corners, we know 3 of them already. There's Bun-G and Hecke G. And we have this map, P prime. And horizontally, we just have the graph of Frobenius. So any stack over FQ, there's a Frobenius morphism that raises functions to the qth power. So here's for S on the level of functions raises everything to the qth power. So it's FQ linear. In particular, I applied to Bun-G. Okay. So now this is defined as at least as a functor of points. We know how to calculate Shtuka G using this diagram. So let's do that calculation. So S point means a point in Hecke G, which in turn means a quadruple data. Let me just very brief, just abbreviate this complement of a point by x, remove x, although this really is an S family version. Let me, oh, sorry, not the end. This is only the data given to you by the Hecke part. And then that automatically gives you 2 bundles, mapping to the lower right corner. Then on the lower left corner, you have another bundle, which is not a new bundle. It's just the first bundle here. Okay, so because it's identical to the first bound factor. But another requirement is that Frobenius Bun-G applied to this first bundle has to be isomorphic. You have to give an isomorphism between Frobenius image of E and the second bundle. Okay. So this is just mechanically reading off from that diagram. We obtain this description of S points. So this last piece is also a data. This is an isomorphism that you have to give. Now, usually we write it in a slightly different way. Equivalently, we like to write it in the following, as a following diagram. Alpha is so this dash arrow means it's not defined everywhere. This is away from a point. This is a small x. And then the second bundle is already determined by the first bundle. So as the image under Frobenius morphism. So I use this left exponent tau to denote image under Frobenius. But more concretely, what it means is if you look at the map from x times s to x times s, which is identity on x and the Frobenius on s, I just pull back the bundle along this map. Okay. So I'm kind of contracting the data of E prime with this isomorphism, so I didn't have to introduce E prime. Now this is the equivalent data. Okay. A meromorphic isomorphism between E and its Frobenius pullback away from one point, one moving point. So this is relatively easy to define. Again, it does not have good geometric properties. It's still as infinite as that Hecke. So next, let me introduce bounds. So the bounds are some constraints on the on this isomorphism. Okay, so we want to say what order of poles alpha is allowed to have. So this to introduce bounds, I need to review Alphan-Grossmannian and its stratification. Okay. So for GLN, Alphan-Grossmannian, at least if I just talk about its k points, this as a set is very easy to describe. These are just O lattices in, let's say, well, this is a local. So this is depending on a local field. So everything is happening near x. So this is lambda is an OX submodule of rank n, of the full rank submodule inside a given n-dimensional vector space over local field. So yeah, we already heard from Pierre Henry's talk. This can be presented as G of fx mod G of Ox. Okay, so this an element G here corresponds to G acting on the standard lattice. It's a bijection. And now we introduce stratification, or rather first a decomposition of GER-G just on the level of sets. So GER-G lambda, let me be very concrete. So lambda is a tuple D1, Dn, D1 decreasing sequence of integers. And it's easier to define the case where all of them are non-negative. Then in lambda, lambda k points classify those lattices that are already contained in the standard lattice, such that if you look at the quotient, so this is some torsion O module. If I pick a uniformizer T at x, it acts here by a nilpotent operator. And so the requirement is the Jordan type of this nilpotent operator. As Jordan blocks D1, D2, up to Dn. So that's very concrete description. And what if one of the di's is negative? Well, you just shift. In general, you can add some d to make it a positive, and then GR of lambda plus d. So suppose this is totally positive. This will be those lattices that are of the form t to the minus d times those lattices that are classified by GR lambda. Now you shift it, you enlarge it, this operation, so that these lattices will not necessarily be in the standard lattice. And as lambda varies, we do get a decomposition. So lambda is just all the integer and tuples satisfying this decreasing condition. Okay, so this is what happens for GLN. So general G, first, GR G is defined as a its quotient. So again, I'm choosing a uniformizer at one place. But in fact, this result is intrinsic to the local field. It doesn't depend on the choice of the uniformizer. But it's convenient to choose one and think of this as an infinite dimensional group where matrix entries, say G is a matrix group, matrix entries are Laurent, formal Laurent series in T. And then it has a subgroup where entries are formal power series. And you carefully make a quotient in. Yeah, so this is a group functor whose k points is k bar double bracket T. But this can be defined for when k is replaced by k algebra. You just replace here as well. And there's some technicalities going into defining the quotient. And to show this really is a reasonable object. So I'll just say, state it as a fact. At least if you only care about the reduced structure, this is a union, a countable, but infinite union of projective varieties. Okay.
The question on Discord about why the affine Grassmannian is called affine.
The question is why the affine Grassmannian is called affine. So the affine comes from replacing the base field by formal Laurent series. This is following the kind of tradition, following the convention in, like, say, the algebras. We have affine Kac-Moody Lie algebra, which is an infinite dimensional version of finite dimensional Lie algebras. And from passing from finite dimensional Lie algebras to affine Kac-Moody algebras means you're adding double brackets. That comes from, it does not mean that this variety is affine. But indeed, it's a union of projective varieties. And we can already see it from this GLN case, maybe here. If I look at this more concrete description, you can easily recognize it as some subvariety in a Grassmannian variety, because implicitly this lambda will have to contain t to some t to the d1 some rescaling of the standard lattice, because the longest Jordan block has size d1. So lambda is between these two lattices. There's only finite dimensional degree of freedom over the residual field for lambda. So the choice of lambda is some subspace in a fixed finite dimensional vector space. So it's a subvariety in the usual Grassmannian. Okay, closed subvariety in the usual Grassmannian, and therefore projective variety. Okay, so now the decomposition into lambda is generalizes also to arbitrary G. On the level of varieties, this is a stratification indexed by dominant co-weights. So here, I choose a maximal torus. It has a co-character lattice, and this plus means dominant. So I'm only looking at those lambda whose pairing with any simple root is non-negative. Okay, so this is a stratification. Not a disjoint union of varieties. Okay, so it makes sense to talk about GR less than equal to lambda. This is by definition the closure of GR. Let me subtract G now, so just closure. And this contains, this is the union of GR lambda prime such that the lambda prime is in the negative obtuse cone of lambda. Okay, so this is the, you subtract from lambda some linear combination of co-roots, positive co-roots. So that's the partial order you put on this set. Okay, so this is a projective variety. Projective variety of dimension 2 row paired with lambda. So now we can talk about the bounded version of Hecke. Roughly speaking, this Hecke will map to Grassmannian, affine Grassmannian. It's not literally true, but let me try to make sense of this map. So according to the moduli meaning, Hecke classifies X. Let's fix a point first. Then this point is not in the data anymore, so it's just meromorphic isomorphism of two bundles away from X. From this data, we want to get some local data, which is, I can just restrict E to the formal disk around X. Again, restrict alpha to the formal puncture disk. This is on the, alpha is only on the puncture disk. So here, puncture disk is a spec of Fx. Dx is a spec of Ox. Again, this is a little bit sloppy because I didn't input a test scheme here. I'm pretending I'm just describing K points. So from the global data, we restrict to the formal disk. We get two G bundles on the disk together with an isomorphism away from the center of the disk. And this thing is very close to affine Grassmannian already. In fact, since it's so important, let's give it a name. Q, some quotient version of affine Grassmannian. This is the definition of quotient affine Grassmannian. Concretely, what it is instead of quotienting the group G power series T on one side, I quotient on two sides. So this may look like a bad idea at first because we have some infinite dimensional variety, which is already a little bit scary. And now I quotient it by infinite dimensional group. And it's so not even clear what the dimension of this guy is. Now, but in fact, this is, in many aspects, this is more natural than the affine Grassmannian. For example, later we'll talk about geometric Satake. It's better to think of those sheaves in geometric Satake as living here, which is more symmetric. Okay, so there's a map from Hecke X to some quotient version of Grassmannian. And yeah, so the question was, is it possible to give a definition of this map? No? Oh, as a functor. Okay, the double quotient as a functor. Yeah, so you have to sheafify, but before you sheafify, it's just so let's say evaluate on a K algebra. It's just a naive quotient as a groupoid. And then you kind of sheafify. I don't know how much this helps. Okay, but so the canonical recipient of this kind of desirable map is some quotient version of Afan-Grassmannian. So this is good now because our stratification, yeah, I forgot to say actually the most basic thing about stratification. This is, each piece is in fact a left orbit. It's orbit for the left action of G square bracket T. So in that definition, also here, there is a left action by the whole loop group. But if you look at just action by G square bracket T, orbits are exactly parameterized by dominant co-weights. So this stratification is a very natural one. And certainly it descends to the quotient, because those are just points on this quotient. So I can talk about Q GER less than or equal to lambda, for example. This makes sense. And so I have this evaluation map at X, I call it evaluation or restriction, just restrict to the formal disk. I can define Hecke X less than or equal to lambda to be the preimage of Q Grassmannian less than or equal to lambda. So what does yeah, okay, so this is the case where X is fixed, little point X. We also have a version where X moves, but I don't want to go into the details. There's also a can you say it a little bit louder?
I mean, you have defined the strata on Afan-Grassmannian.
Yes.
Is the strata finite dimensional?
Yes. Yeah. The question was whether these strata on the Afan-Grassmannian are finite dimensional. Yes. The answer is the dimension is precisely this number. Oh, dimension of the Hecke stack. So you want to know dimension of Hecke X less than or equal to lambda. So this is dimension of bond G plus that extra dimension coming from GER lambda. And this is also very concrete. It's dimension of G times genus of the curve minus 1. So if we let X move, there's still a way to produce an evaluation, kind of universal evaluation map. Now I can't say Q GER X, because X is moving. But so to make sense of it, you have to pass to a further quotient of it, where to make it independent of the point. So this is so you divide by another infinite dimensional group to make it canonical. This is the automorphisms of the formal disk. So this is not essential. So you should just accept that there is a version Hecke less than or equal to lambda that looks like Hecke sub X less than or equal to lambda over every point X. So let me give an example. Again, for GLN, and lambda is this simplest dominant co-weight. Then what we are talking about, it classifies a pair of, so a point X, pair of vector bundles, V and V prime, and their relative position is that the second bundle is slightly smaller than the first. So the condition is, so this is map alpha, and co-kernel of alpha is supported on the graph of X, and is free of rank 1, locally free of rank 1 there. So it's a skyscraper sheaf, the co-kernel skyscraper at X. That's the in some sense, most common kind of modification that you see in automorphic forms. Okay, so now we can define bounded version of Shtuka. Okay, so I reserve subscripts for something else and put it in the superscript. This again is just defined by the same Cartesian diagram, except you put a bound on Hecke. Okay, so that's definition. Now, there's if you compute what happens to this example, try to compute what Shtuka less than equal to lambda is, you end up with so moving point X, then V, and then V prime is the Frobenius pullback of V, and it's required to be a subbundle, subcoherent sheaf whose degree is 1 less than V. So that's given by this Cartesian diagram. Well, it's more precise, but in particular, the degree is 1 less. The co-kernel has to be supported on X. But then you quickly find a contradiction. How could Frobenius pullback of a bundle change the degree? So this is not the Frobenius on the curve. This is a Frobenius on the test scheme, on the coefficients. So this is impossible, which means for this particular lambda, if you put the bound, the Shtuka moduli space is empty. So that's not very exciting. So that the reason for that is our choice of well, there are two ways to fix this issue. One is you choose another lambda. For example, it will not be empty if you work with this lambda. The point is the sum of these integers should be 0 in order for this bundle and this bundle to have the same degree, in order not to violate this constancy of degree. Or you can introduce iterated version. You can have some intermediate bundle between V and Frobenius pullback of V that is, let's say, degree 1 smaller than both. That also works. So, yeah, so let me introduce the iterated version. Again, this is not the most general iterated version. We start with Hecke iterated version. Let me just Iterated means I make R steps of modifications. So this means first I need to specify R points. And then I have G bundles, R plus 1 G bundles. And they are related by these isomorphisms away from the corresponding point. So this is on X, remove X1. This is on X, remove X2. Isomorphism on this complement. And alpha R. Okay, so this is the unbounded iterated Hecke stack. And then it's easy to define the bounded version. So you just need to put a bound in each step. Okay, so you need to specify some lambda now is a tuple of dominant co-weights. So that gives some iterated version of Hecke. And then using the same Cartesian diagram, we get Shtukas. Okay, so let me give an example. Simplest example in GL1. For the iterated version. So for GL1, what is the choice of lambda I is just an integer. And then Shtukas. Well, and the partial order on this co-character lattice is trivial. There's no way to compare any two of them. So I just write lambda. So that means I'm considering our points and line bundles. And the last one is isomorphic. I'm given an isomorphism between the last one and the Frobenius pullback of the first one. So this is the unbounded version of Shtukas. Now I put a bound to each of these maps. So this alpha 1 has to, for a map between line bundles, I can talk about its divisor. So it records the order of zeros in poles. Here, divisor of alpha 1 should be, maybe negative of it should be lambda 1 times, so up to sign should be lambda 1 times x1, etc. Okay. Well, this is extremely concrete because we are working with line bundles. For line bundles, if you fix the modification type, so this lambda I, your next line bundle is uniquely determined. So you just twist your original bundle by some multiple of the point. So you can inductively determine all these bundles. So LR is isomorphic to I think there's a minus sign here. To L0 twisted by a divisor. And then in the end, you impose an equation that this last guy, L0 twisted by a divisor, is you're given an isomorphism with its own Frobenius pullback. So all in all, you can rewrite this stack in terms of the following Cartesian diagram. You have R points on the curve. It gives you a divisor. It's linear combination. So these lambda i's are fixed. So you get a divisor that in particular gives you a line bundle. So the O of that divisor and then you want to solve the equation that tau of L0 tensor L0 inverse, their difference is equal to this divisor. Okay, so your choices of L0 is the solution to this equation, which is fibers of this Lan isogeny. So here it sends L0 to tau L0 tensor L0 inverse. To any algebraic group, there's such an operation. It's called a Lan isogeny. And then you just base change. You get Shtuka, bounded iterated version for Shtuka, GL1. So from this diagram, we see we can read off some geometric property of GL1 Shtuka. Yes. The question was whether this definition depends on all the points being k points. The answer is no. You can work with, well, so these points, it doesn't even make sense to ask whether they are rational points because these are moving. So these are S points of X. They're part of the moduli problem. So yeah, it's anyway. Okay, so we get some corollary. First, this line map sends whatever line bundle to a line bundle of degree 0 because tau of L0 and L0, they have the same degree. So since this line map lands in pick 0, it will not meet the image of x to the r unless the sum of the coefficients is equal to 0, unless you make up a degree 0 divisor, which would land in pick 0. So if this sum is not equal to 0, then we conclude this fiber product is empty. So this is a similar phenomenon to the emptiness here. Okay, we did not choose a correct lambda. Now, on the other hand, if their sum is 0, and R is non-empty, well, R is at least 1, then, well, or even R is, so when the sum is 0, we can see this is non-empty. It's non-empty because the Lan isogeny actually surjects onto pick 0. And more precisely, Lan isogeny is just a finite tau cover of, it's a universal abelian cover of Picard. So we get that the map from Shtuka to x to the r. By the way, these xi's are called the legs. So I didn't mention this. This map is actually a torsor for the deck transformation group of the Lamb isogeny, which is of FQ points of Picard X. Again, this has a little bit of automorphism, FQ star. This itself is a groupoid, and each fiber of this map is isomorphic to a copy of this discrete groupoid. Okay, I stop here.
Maybe we have a couple of questions.
Yes.
So all of the Frobenius morphisms were absolute Frobenius, right?
The question is whether all Frobenius maps are absolute Frobenius. So yeah, so absolute you mean, well, I said exactly what they are. They are just raising all functions to the qth power.
Yes, which in particular is not a K morphism, right? It's not a morphism of K schemes.
It is, because K is FQ.
I thought it was only that, well, is Q a prime or a power?
Q is a power of prime. So raising F to the qth power, not pth power. Yeah.
Other questions?
Yes. Oh, okay.
Could you say something about why the Hecke stack is called Hecke?
Why the Hecke stack is what?
Why does it have the name Hecke appear? Like, what does it have to do with Hecke operators?
Maybe let's leave it to the Q&A.
Yeah, can you give a more specific description of lambda equals 1, 0, 0, 0, minus 1?
This I can do it more quickly. So the question is when lambda is equal to 1, 1, 1, 0, 0, minus 1, what does a modification of that type looks like? So such a modification means at the level of just pointwise, it means so bounded by lambda means if you intersect them, well, this is a subsheaf in both. Then you look at how much this degree decreases. This is by at most 1. Okay, so it may be they are equal. That's allowed. That's the less than or equal to part, the equal part. When it's strictly type lambda, then this intersection will have exactly 1 degree 1 less than each of them.
Okay, I think let's thank Zhiwei again.